It is very hard for archaeologists to explain how that was done using purely leverage and mechanical advantage.
When Graham Hancock walked into
For more than 4 decades, Graham Hancock has occupied a unique position in the world of ancient history. To his supporters, he is an investigator willing to ask the questions others avoid. To many archaeologists, he is a controversial outsider whose ideas often extend beyond what the available evidence can support. A former journalist turned independent researcher, Hancock has spent much of his career exploring the mysteries of ancient civilizations and challenging long-established interpretations of Egypt's past. His best-selling books, including Fingerprints of the Gods and Magicians of the Gods, introduced millions of readers to alternative ideas about humanity's distant history, while also drawing strong criticism from mainstream Egyptologists who argue that many of his broader conclusions remain speculative. Yet, despite decades of criticism, Hancock has continued traveling to archaeological sites, consulting engineers, geologists, and materials specialists, and searching for answers to one of ancient Egypt's greatest mysteries. How did the Egyptians cut and shape granite with such extraordinary precision? In recent years, Hancock turned his attention toward a new line of investigation, working alongside material scientists and researchers to examine ancient granite surfaces using modern analytical techniques. The research focused on the possibility that Egyptian craftsmen used advanced abrasive methods, including mineral-based slurries, to achieve the remarkable precision seen in their stonework. But before we uncover the evidence behind Hancock's latest claims, take a moment to subscribe to the channel and help us reach our goal of 5,000 subscribers. Now, let's dive into the discovery that has reignited the debate over how ancient Egyptians mastered granite. Unlike the limestone blocks that make up most of the Great Pyramid, granite presents an entirely different challenge. It is one of the hardest natural stones on Earth, containing large amounts of quartz that make it extremely resistant to cutting and shaping. Even today, professional stonemasons rely on diamond-coated tools and powerful machinery to produce clean, accurate cuts. Yet more than 4,000 years ago, Egyptian craftsmen produced enormous granite sarcophagi, statues, columns, and blocks weighing dozens of tons. Inside the king's chamber of the Great Pyramid, massive granite blocks fit together with astonishing precision. At the Valley Temple near Giza, joints between granite stones are so fine that even modern visitors struggle to insert a thin blade between them. Ancient drill cores recovered from Aswan display perfectly formed spiral grooves that continue to puzzle engineers, because the cutting patterns appear unusually efficient for the tools traditionally attributed to the Egyptians. For more than a century, the standard archaeological explanation has remained largely unchanged. According to conventional theory, Egyptian craftsmen cut granite using copper saws and tubular drills combined with quartz sand as an abrasive, while shaping the stone with hard dolerite pounding stones. Archaeologists have demonstrated that these methods can indeed remove granite, although slowly. However, Hancock argued that the surviving artifacts seem to display a level of speed, consistency, and precision that appears difficult to explain through these techniques alone. Copper is far softer than granite, and experimental archaeology has repeatedly shown that copper tools wear rapidly when used with ordinary sand. While this does not mean the traditional explanation is impossible, Hancock believed it left important questions unanswered, particularly regarding the remarkable finish seen on many surviving monuments. Rather than continuing to argue from observation alone, Hancock has said that recent advances in materials analysis offered an opportunity to examine the stone itself for clues. He has discussed research involving microscopic examination of granite surfaces, suggesting that tiny traces of abrasive minerals may survive within ancient cut marks. According to Hancock's interpretation, these investigations indicate that the Egyptians may not have relied solely on ordinary quartz sand. Instead, he argues they may have deliberately prepared abrasive slurries containing much harder minerals capable of dramatically increasing cutting efficiency. In Hancock's view, this possibility would explain why ancient cuts appear smoother, more accurate, and more consistent than many modern demonstrations using simple sand abrasives. The mineral Hancock has focused on is corundum, a naturally occurring aluminium oxide that ranks just below diamond on the Mohs hardness scale. Today, synthetic corundum, commonly known as alumina, is widely used throughout industry as a powerful abrasive for grinding and cutting extremely hard materials. Hancock argues that if ancient Egyptian craftsmen intentionally incorporated finely ground corundum into water-based abrasive slurries, the cutting process would become vastly more effective while allowing relatively soft copper tools to act primarily as carriers that guided the abrasive rather than cutting the granite directly. In this interpretation, the abrasive performs most of the work, while the copper tool simply maintains pressure and direction. To explore whether this idea could account for the archaeological evidence, Hancock has described experimental trials in which copper tools were used with different abrasive mixtures. According to his account, ordinary sand produced slow cutting rates and significant tool wear, while harder abrasive mixtures performed noticeably better. Hancock has argued that copper tools combined with corundum-rich slurries generated cleaner cuts, reduced wear on the copper, and produced drilling marks that more closely resembled some ancient Egyptian granite cores. He presents these experiments as evidence that sophisticated abrasive technology deserves greater consideration within discussions of Egyptian stoneworking. It is important to note, however, that these conclusions remain disputed. While many engineers and materials scientists agree that harder abrasives would naturally improve cutting performance, mainstream Egyptologists have not broadly accepted Hancock's interpretation as established fact. Archaeologists continue to debate whether the microscopic traces attributed to corundum represent evidence of ancient manufacturing methods, later contamination, or another process altogether. Likewise, questions remain regarding whether sufficient archaeological evidence exists to demonstrate that corundum was intentionally sourced, processed, and used on the scale required for pyramid-age construction. At present, the idea remains a hypothesis rather than an accepted consensus. Even so, Hancock argues that the broader lesson extends beyond the specific question of corundum. He believes ancient Egyptian craftsmen possessed a far more advanced practical understanding of materials, abrasives, and manufacturing than modern audiences often assume. Rather than imagining mysterious machines or impossible technologies, Hancock suggests that generations of experimentation may have produced highly refined industrial techniques that simply were never recorded in surviving texts. Whether future research ultimately confirms or rejects his interpretation, the debate has encouraged scientists, engineers, and archaeologists to re-examine ancient granite with modern analytical methods. In that sense, the mystery of how Egypt's master stoneworkers achieved such extraordinary precision remains one of the most fascinating questions in archaeology, and one that continues to inspire fresh investigation. In other words, success did not depend on a miraculous material. It depended on knowledge. The abrasive itself was only one part of the process. The craftsman had to understand how to prepare it, how to keep it suspended in water, how much pressure to apply, and how to feed the tool through the stone without allowing the cutting surface to glaze over. Every variable mattered. Every mistake reduced efficiency. It was a manufacturing process refined through experience, not brute force. If Hancock's interpretation is correct, then this changes the conversation entirely. The mystery was never that the Egyptians possessed impossible technology. The mystery was that modern researchers had been looking at the wrong part of the process. For decades, nearly all attention had focused on the copper tools themselves. But according to Hancock, the copper was never intended to do the cutting. It simply held the abrasive in place, while an engineered slurry performed the real work. Once viewed from that perspective, many of the long-standing objections begin to look different. It also helps explain why the surviving copper tools appear so ordinary. Archaeologists have often argued that because only simple copper saws and drills have been found, no advanced cutting methods could have existed. Hancock disagrees. He argues that the sophistication was never in the metal. It was in the consumable material that disappeared thousands of years ago. Abrasive slurries made from crushed minerals would leave almost no archaeological trace after 4 millennia. Water evaporates. Organic binding agents decompose. Fine mineral powders disperse into surrounding sediments. Only microscopic residues trapped inside the granite itself would remain. That possibility is exactly what made the microscopic analysis so important. Rather than searching for missing tools, Hancock argues researchers should examine the stone. Every cut, every drill hole, and every polished surface preserves a record of the manufacturing process. Like fingerprints left behind at a crime scene, the microscopic scratches, embedded particles, and wear patterns reveal how the work was actually performed. To Hancock, this represented the first physical evidence that could directly test competing explanations. Instead of debating theories, researchers could compare microscopic signatures left by different abrasive mixtures with those found on ancient granite. If the patterns matched, the technique became plausible. If they did not, it could be ruled out. For Hancock, this transformed the discussion from speculation into experimental archaeology. The implications extended well beyond granite itself. If Egyptian craftsmen deliberately selected specific minerals for industrial purposes, then they possessed a far more sophisticated understanding of material properties than they are usually credited with. They would have recognized that different abrasives served different purposes, that particle size affected cutting speed and surface finish, and that tool performance depended as much on the abrasive as on the tool holding it. That kind of knowledge does not appear overnight. It develops over generations of observation, experimentation, and refinement. A craftsman discovers that one mineral cuts faster than another. His apprentices improve the mixture. The next generation learns how finely to grind it. Eventually, what began as trial and error becomes a highly developed manufacturing tradition passed from master to apprentice. By the time the Great Pyramid was constructed, Hancock argues, those techniques may already have been the product of centuries of accumulated experience. Whether this interpretation ultimately becomes accepted or not remains an open question. Many Egyptologists continue to argue that the existing archaeological evidence supports conventional explanations, while others believe the new material deserves further investigation before firm conclusions can be drawn. Even so, the debate itself has shifted. Instead of asking whether granite could be cut with copper tools alone, researchers are increasingly examining the role that engineered abrasives may have played. For Hancock, that shift is significant. For 40 years, he argued that something was missing from the standard explanation. Now he believes the missing piece has finally begun to emerge, not through speculation about lost machines or impossible technologies, but through microscopic evidence preserved inside the granite itself. More significantly, Hancock argues that the corundum hypothesis demonstrates the value of interdisciplinary collaboration. For decades, the question of how the Egyptians worked granite remained largely within the domain of archaeology. Archaeologists naturally focused on excavation, inscriptions, and the artifacts themselves. Engineers focused on structural design. Material scientists studied modern manufacturing. Rarely did all three disciplines examine the same evidence together. Hancock believes that was the missing ingredient. According to him, understanding how granite was cut is not purely an archaeological question. It is fundamentally a problem in materials engineering. That is why, rather than relying solely on traditional archaeological interpretation, Hancock sought the expertise of tribologists, mineralogists, mechanical engineers, and specialists in surface analysis. Their tools were different. Instead of measuring pyramids with tape measures or studying hieroglyphs, they examined microscopic wear patterns, analyzed mineral residues trapped inside granite surfaces, and compared them with experimental samples created under controlled laboratory conditions. Every scratch, every embedded particle, every microscopic fracture became a clue to the manufacturing process used thousands of years ago. Hancock argues that this represents a completely different way of approaching ancient technology. Instead of beginning with assumptions about what ancient people could or could not do, researchers begin with the physical evidence itself. The stone becomes the historical document. Unlike written records, granite cannot exaggerate, omit details, or rewrite history. Every cut preserves a microscopic record of the forces, abrasives, and tools that created it. If modern analytical equipment can decode that record, then the stone tells its own story. According to Hancock, this is precisely why the debate has become so significant. It is no longer simply a disagreement over historical interpretation. It is a question that can be tested experimentally. If one proposed method leaves microscopic signatures that match the ancient artifacts while another does not, then researchers have an objective basis for comparing competing explanations. In Hancock's view, this moves the discussion away from opinion and towards repeatable scientific investigation. He also believes the implications reach far beyond the pyramids. If the Egyptians understood how to engineer abrasive mixtures, control particle size, optimize cutting speed, and minimize tool wear, then they possessed a practical knowledge of material science that has been consistently underestimated. They may not have expressed that knowledge through modern scientific equations or textbooks, but they demonstrated it through results. Every precisely fitted granite block, every perfectly drilled core, and every polished sarcophagus becomes evidence of a manufacturing tradition refined over generations. Hancock often points out that technological sophistication should not be measured solely by the presence of electricity, steel, or computers. A civilization can achieve remarkable engineering using entirely different principles. Ancient Egyptian craftsmen may have lacked modern machinery, but they possessed thousands of years to observe, experiment, and improve their techniques. Generation after generation could refine methods, identify superior minerals, develop better abrasive mixtures, and pass that knowledge directly from master craftsmen to apprentices. By the Fourth Dynasty, those techniques may already have represented centuries of accumulated industrial experience. If that interpretation proves correct, it changes how we think about technological progress itself. Rather than viewing history as a simple ladder where each civilization is automatically more advanced than the last, Hancock argues that knowledge can be highly specialized. Modern society excels in electronics, computing, and automation. Ancient Egypt may have excelled in practical stone engineering, precision craftsmanship, and large-scale construction using techniques specifically adapted to the materials available to them. Different technologies, developed for different problems, but impressive in their own context. At the same time, Hancock acknowledges that many questions remain unanswered. If corundum really formed part of Egyptian abrasive technology, where exactly was it sourced? Which trade routes supplied it? Were different grades reserved for different tasks? Did workshops maintain closely guarded recipes for preparing abrasive slurries? Were there royal workshops whose craftsmen possessed techniques unavailable elsewhere? These are questions that only further archaeological discoveries and additional laboratory analysis can answer. Mainstream Egyptologists remain divided on these issues. Many researchers continue to argue that the evidence is insufficient to establish widespread use of corundum abrasives and that alternative explanations remain possible. Others agree that the microscopic evidence deserves closer examination, even if they are not yet convinced by Hancock's broader conclusions. What both sides increasingly recognize, however, is that advanced analytical techniques now offer opportunities that simply did not exist a generation ago. Methods such as scanning electron microscopy, elemental mapping, Raman spectroscopy, and three-dimensional surface metrology can reveal details invisible to earlier investigators. For Hancock, that may ultimately be the most important outcome of all. Whether every aspect of his hypothesis is eventually confirmed or revised, he believes the debate has encouraged researchers to ask better questions and to examine ancient artifacts using technologies capable of revealing information hidden at the microscopic level for thousands of years. In his view, history advances not by defending old assumptions, but by continually testing them against new evidence. The granite monuments of Egypt have remained almost unchanged for more than 4,000 years. They have silently preserved the marks left by the craftsmen who shaped them. Hancock argues that modern science is only now beginning to learn how to read those marks. If he is correct, then the greatest discovery is not that the Egyptians possessed mysterious machines, but that they developed a remarkably sophisticated understanding of materials, abrasives, and precision engineering, knowledge that modern archaeology is only beginning to appreciate. For thousands of years, those granite monuments have stood as silent witnesses to human creativity, preserving the marks of the craftsmen who built them. Every perfectly aligned surface, every carefully drilled hole, and every precisely fitted joint represents a decision made by people whose names have mostly been forgotten, but whose skills remain visible. Whether those achievements came from a lost technique, a refined traditional method, or a combination of both, the evidence shows one undeniable truth. Ancient Egyptian builders were not simply moving stones. They were solving complex engineering problems with remarkable intelligence and discipline. The debate surrounding granite cutting ultimately forces us to reconsider how we define technology. Technology is not only electricity, machines, computers, or modern factories. Technology is the ability to apply knowledge to solve problems. It is understanding materials, controlling processes, improving efficiency, and creating repeatable results. By that definition, the ancient Egyptians demonstrated technological sophistication in ways that deserve serious study. The greatest mistake, Hancock argues, is assuming that ancient societies were limited simply because they lacked modern tools. A copper saw may appear primitive compared with a modern diamond blade, but the effectiveness of any tool depends on the complete system surrounding it. The material being cut, the abrasive being used, the technique of the craftsman, and the knowledge passed through generations all determine the final result. A modern engineer looking only at the copper tool might conclude that such precision was impossible. But an ancient Egyptian craftsman may have viewed the tool differently. The copper was not the technology by itself. The entire process was the technology. The selection of minerals, preparation of abrasives, control of pressure, measurement techniques, and the experience required to repeat the same results thousands of times. This perspective changes the way we look at other ancient achievements as well. Across the world, civilizations left behind structures and artifacts that continue to challenge researchers. Massive stone monuments, precise astronomical alignments, complex metalwork, and advanced architectural techniques all suggest that ancient people possessed specialized knowledge that is sometimes difficult to reconstruct because the original methods were never written down. Much of ancient knowledge was practical rather than theoretical. A master craftsman might know exactly how a material behaved without having a modern scientific explanation for why it worked. A builder might understand proportions, balance, and structural forces without using modern engineering terminology. A metalworker might create exceptional alloys through generations of experimentation without knowing the atomic structure of the materials involved. Human knowledge has always developed this way. Observation comes first. Explanation often comes later. This is why the study of ancient technology requires humility. Modern civilization has achieved extraordinary things, but technological progress is not a straight line where every generation is superior in every area. Different societies developed solutions for different challenges. Some knowledge survives and evolves. Some disappears. Some remains hidden until new tools allow us to recognize it. The Granite mystery represents a larger lesson about history itself. The past is not a simple story of primitive humans slowly becoming modern. It is a story of countless generations experimenting, adapting, and creating solutions with the resources available to them. The ancient Egyptians did not need computers to understand stone. They did not need modern factories to develop precision. They needed curiosity, patience, skilled hands, and generations of accumulated experience. Whether future discoveries fully confirm Hancock's interpretation or reveal a more complicated explanation, the search itself has value. Every new analysis, every experiment, and every technological breakthrough gives researchers a better opportunity to understand how ancient people achieved what they achieved. The question is no longer simply, how could ancient people do this? The better question is, what knowledge did they possess that we have not yet fully understood? Because history repeatedly shows that human creativity is far older and more diverse than we often imagine. The granite monuments of Egypt remain among the greatest examples of ancient craftsmanship ever created. They survived earthquakes, wars, and thousands of years of changing civilizations. They continue to challenge engineers, inspire researchers, and remind humanity that the past still holds unanswered questions. For generations, the precision of Egyptian granite work was viewed as one of archaeology's greatest mysteries. Now, through the combination of archaeology, material science, and experimental research, a new possibility has emerged, that the ancient Egyptians may have achieved their remarkable stonework through a sophisticated understanding of abrasive technology and craftsmanship. The mystery may not have been about lost machines or impossible inventions. It may have been about forgotten knowledge, knowledge created by skilled human hands, refined through centuries of experimentation, and preserved forever in the stone monuments that still stand today. For 40 years, the question of how ancient Egyptians achieved such extraordinary precision in granite remained one of archaeology's most fascinating mysteries. The explanations existed, but many believed they did not fully account for the evidence carved into the stone itself. The unusual drill marks, the perfectly aligned cuts, and the remarkable smoothness of ancient granite surfaces continued to raise questions that challenged researchers to look deeper. Now, through the combination of persistent investigation, advanced material analysis, and experimental archaeology, Graham Hancock argues that a missing piece of the puzzle has finally been revealed. Not an explanation based on impossible machines or lost science fiction technology, but a method built on a deeper understanding of materials. According to Hancock's interpretation, ancient Egyptian craftsmen may have used corundum-based abrasive slurries, a sophisticated cutting technique that relied on knowledge of mineral hardness, carefully prepared mixtures, and generations of practical experimentation. This process would have required more than simple tools. It would have required an understanding of how different minerals interacted, how abrasives could be prepared, and how skilled craftsmen could control the cutting process with extraordinary precision.